Okay, so when we left off, we were talking about FIR filter implementations. We have this kind of generic direct form implementation that we already talked about, and basically an arbitrary set of filter coefficients. But what I'm interested in most of the time with FIR filters are these constant delay filters, where I know that the phase shift in every single frequency is just proportional to the frequency along the time delay. Basically, same time delay for every possible frequency means it's easier for me to get a hold of things like time delays through a filter. It's easier for me to line up the output samples of a filter with the input samples in time. And so it's actually a pretty useful and powerful thing, and it's something that we have trouble doing either with continuous time filters or with the IIR discrete time filters. But for the FIR filters, we're almost always going to use constant delay filters. And so if we want a delay that's independent of frequency, there's a couple of cases that are kind of easy to just write down, right? So I can give you some examples of constant delay filters. First example is where h of e to the j omega is real, right? Meaning zero phase shift for all frequencies. And there at my output, there's no time delay at all if there's no phase shift in the harmonics. And so if I have a real function for my transfer function, there's no phase shift and there's no delay in the filter. Okay, and so and we already talked a little about some symmetry properties in the transform. If my transfer function is real, here, what that boils down to is my impulse response must be symmetric. Right? Which means I have even symmetry here. H of minus n has to be exactly the same as h of n. Okay? So there's an easy example of a filter that has constant delay. There's another important example, and that's where instead of just using a real transfer function, I might choose to use a purely imaginary transfer function. So h of e to the j omega is purely imaginary. Right, and if we look back at kind of DFT or DTFT properties, we end up saying, okay, well, h of n in the time domain satisfies an odd symmetry, is odd symmetric. Okay, which means if I look at h at minus n, that has to be negative of whatever I see at h of n. It has an odd symmetry around the origin. Okay, so these two cases are kind of the fundamental ones. These two examples are the fundamental starting point for talking about constant delay filters. Here I have zero phase shift. Here I have a constant 90 degrees phase shift, but it doesn't depend on frequency, so the time shifts are all symmetric. I use these usually when I'm designing something that's going to just attenuate a band of frequencies. Band pass, band reject filters will typically have symmetric impulse responses. On the other hand, if I'm trying to build something where I have, kind of the classic example of one of these is where I'm trying to build a filter that estimates the derivative of a signal. Well, there I want a transfer function that is purely imaginary, j omega, right, for the transfer function. So that's a good example of a case where I might go with the second one. Now, there's an obvious gotcha here with these two. Neither of these two filters is causal, right? Okay, these are filters with zero delay, and kind of the key is if I'm talking about finite impulse response filters, if I satisfy one or the other of these, I can come up with a causal filter by just taking this impulse response that I designed with zero delay and delaying it out. And then instead of having a zero delay filter, I end up with what we're after, a constant delay filter where every frequency goes through at exactly the same delay. It'll be the amount that we deal with. So if I look at constant delay filters, they tend to be variations on one or the other of these two themes. Okay, so we're just going to put that down as a definition. So here we're going to say an FIR filter is said to be constant delay. Or sometimes you'll say linear phase. If its impulse response satisfies one of the following, right? And then there are kind of these two cases that I look at for the impulse response. And you just unfold here so I can get a little more space going. Okay, so if it's impulse response, my first case is where we said I had a symmetric impulse response around some point, right? Here it's around the origin, so I had a zero delay, but it doesn't matter if I delay the filter response out a little bit, I still have a constant delay filter. So that case is where h of n is exactly the same as what I look at when I look at the other side of the array, h of, and I'm going to put the indexing down here, okay, and that's got to be true for all the values of n that make sense. So this is n equals 0, 1, all the way out to m minus 1. Okay, so there's my symmetric impulse response. That's the first value of the impulse response is the same as the last. The second one's the same as the second to last, and so on, all the way down until you get to the middle of the array. That's one case. That was my first case, my real transfer function, probably the more common case. Or the other case was where I had a purely imaginary response. Here I want a negative sign in the mix here. H of n equal minus h of m minus 1 minus n. Okay, for the same values here for n equals 0, 1, out to m minus 1. Okay, so either of those two cases are linear phase or constant delay filters. All right, and almost always we're going to restrict our coefficients to satisfy this. And what it means is when we start talking about designing one of these filters, I don't have really m arbitrary coefficients if I have an m-tapped coefficient filter. Remember, my generic form for the FIR filters look like this, a tap delay line. And I can choose any coefficients I want for all of these taps. The cases we're always going to design are going to have this one equal to this one, or minus, right? And this one equal to the second to last, and this one from the third from the last, and so on. What that means is, you know, if I go to a filter design problem, I need, in order to design this filter, I have a total of m unknown values, m unknown coefficients to solve for to get a good filter out. Well, the truth is, if I'm worried about linear phase filters, there are not m independent unknowns. They're kind of coupled to each other. There's about half of that many unknowns. Okay. All right. So this is my constraint. This is linear phase filters, right? And the ability to have linear phase characteristics is really a major advantage of the FIR filters. And basically, it's often the reason that we talk about FIR filters as opposed to IIR filters. We know we can get really long impulse responses if I have a little feedback in my system and I deal with IIR filters. It's a big advantage. It means I can get very sharp responses if I'm allowed to place poles in the filter. There's a real restriction going to FIR filters. One of the reasons we're willing to go there from a computational point of view is I'm able to pick up this linear phase characteristic. Virtually every FIR filter we design is going to have linear phase. Okay. Okay. One of the little side notes we get along the way for linear phase is that our computational complexity can be reduced, right? And so here, for a linear phase filter, linear phase filter. I'll spell it out. That's not a common abbreviation. FIR filter. The number of multiplications can be reduced. Okay, so a nice little observation is, there's no need for me to multiply by the same number twice if the impulse response is symmetric. And so what I can do is I start off on my tap delay line structure. This is my direct form again. I'm going to have x of n coming in. And just like I did before, I'm going to go through this sequence of delays. And this is going to continue out until I get to the end of the filter. E to the minus 1, and minus 1, and then, so this is my delayed filter. Now, kind of the assumption here is normally I would take this one, remember in my old picture, let me throw this back up here, right? In my old picture, that first weight was times h0, and now we're saying, if it's linear phase, that's exactly the same as this last coefficient. And instead of multiplying this one by h0 and multiplying this one by the same value and then eventually adding them both up, I'm going to add them first and then scale. So I'm going to take this guy and I'll add it to the value I had way out here on this one, right? So these are going to add together, and that result I'm going to multiply by h of 0, right? Okay? And then I'm going to do the same thing here. I'm going to take this guy and I'm going to add it to what I get way out here. And I take that result and multiply that by h of 1. And so on, right? I have another plus sign here, something else out here that gets added to it. H of 2. And the result is I get about the same number of total additions that I need to get, but to generate my output, my filter output, I actually only have to do the scalar multiplication half as often. Saves me some power, saves me a little real estate if I'm putting all this in silicon, saves me some multiply operations. Often in terms of speed of an algorithm in a DSP processor, saving those multipliers isn't going to buy you much because I do a multiply and an add in a single instruction on most DSPs, and so not quite as big a deal when we're on a regular DSP processor, but still some hardware savings and some power savings. Is pretty common in hardware to see that restriction put on your FIR filters. I'll take a break there, and then we'll come back and talk about some other types of filters.